Okay, all right. Let's start today's tutorial session. So we have covered problems based on three modules. The first module was load characteristics and load management, and the second module was the a brief overview of power distribution networks, and the third module was power quality and reliability assessment of distribution networks. So today we are going to solve problems based on the module 4, that is load flow analysis in power distribution networks. So let us see the first problem of today's session. So the first problem is, if a distribution line resistance is 1.5 ohm, determine the per unit resistance considering base kV as 11 kV and base MVA as 100, and the following options are given. So you can also solve parallelly with me. In this problem, what we have given values are line resistance 1.5 ohm and base kV, let denote it as kV base 11 kV, and MVA base for per unit analysis 100 MVA. So for finding out the per unit resistance value, first we will find the Z base per unit, sorry, base value of impedance. Base value of impedance, Z base, kV square divided by MVA base, that will be Z base. So 11 square divided by MVA base is 100. It will give you value as 1.21 ohm. Now you need to find out the per unit value of resistance. Then we can write R per unit. Per unit value is the ratio of actual value to the base value. Actual value divided by base value. Actual value we have R and base value Z base. We have found out. So R is given as 1.5 ohm and Z base is 1.21. It will come out as 1.24. So the correct answer for this first problem is A, 1.24. Yes. 1.24. Now let us see the next problem. It is also based on the per unit system analysis. The second problem is if a distribution line reactance is 0.5 per unit, determine the line reactance in ohm considering base kV as 11 and base MV is equal to 100. So here the values are given in per unit and you have to find the actual value. So similar to the previous question, we have given data as x per unit in 0.5 and kV base 11 kV MVA base is 100 MVA, and so from these values we can find the Z base. So we have found out in the previous question that Z base is 1.21 ohm. So we know that x per unit is actual value, that is x divided by Z base. From here x is x per unit into Z base. So x per unit is given as 0.5 per unit. Z base is 1.21 ohm. So finally we will get 0.605 ohm. So the correct answer for this second problem is D, 0.605 ohm. How many of you have given the correct response? Anu and Payal, both of you are correct. So let us see the next question. So the next question is, which of the following is correct a statement in view of the sequential iterative a step performed in forward backward sweep load flow algorithm? So these are the options given below, and based on the option you have to find out the correct choice. So we have seen the forward backward sweep load flow algorithm for the in the radial distribution networks. So in this algorithm, what we first find out. So the based on the options, A option is firstly line currents are updated in forward sweep and then node voltages are updated in backward sweep. B option is firstly line currents are updated in backward sweep and then node voltages are updated in forward sweep. C option is firstly node voltages are updated in forward sweep and then line currents are updated in backward sweep. And the D option is firstly node voltages are updated in backward sweep and then line currents are updated in forward sweep. So what do you think? This is very easy question. If you have gone through the lecture, then you can easily able to give the answer. So I got many responses B. Yes. So the in the forward backward sweep load flow rhythm, first we will do the backward sweep in which we will determine the line currents. So the line currents are updated in backward sweep and then we found out the node voltages in the forward direction, that is forward sweep. So the correct answer will be B. And let us see the next problem. The next problem is the forward backward sweep load flow algorithm starts with the guess value of. And the options are A option is node voltages of load nodes, B option is node voltage of slack node, C option is load currents of load nodes, and D option is load currents of slack node. Slack nodes means substation node. Where the voltage we have assumed as fixed value. So what we will initial guess in this forward backward sweep load flow algorithm. Yes, Payal, Anu, Pedro, all of you have given answer as A. So this is correct. If you see the flow chart of backward forward sweep algorithm, you can also see that. So first we will just keep this values of node voltage assume to equal to of slack node. So the A option is correct. Visually take it as 1 angle 0 per unit. So let us see the next problem. So the next problem is that which of the following steps needs more computation? And the options are A option is forward sweep, B option is backward sweep, C option is lateral sweep, and D option is downward sweep. So from the here you can easily eliminate these two options C and D, and you have two choices forward sweep and backward sweep. So based on this, which sweep method, which sweep steps needs more computation? What do you think? Payal and Anu have given answer as B. In backward sweep, we usually determine the line currents, and in forward sweep, we determine the node voltages. So we need more computation in backward sweep. So that's why the correct answer is B. Backward sweep is the correct choice. And let us see the next problem. The next problem is the following parameters are specified for load nodes of radial distribution networks. And the options are active and active power, B option is voltage magnitude, C option is voltage angle, and D option is power loss. Yes. Pedro, Palvi, Payal, Anu. Yes, correct answer is A, active and reactive power. So at the nodes, we know the how much power demand is there, and we have to find the node voltage using forward and backward sweep load flow algorithm. So the known values are active and reactive power. So these are the specified for load nodes of radial distribution network. So for this 6 number problem, A is correct option, active and reactive power. Now let us see the next problem. The next problem is that the power demands of a node for a radial distribution network are 80 kilowatt and 60 kVAR. Assuming that the base volt ampere is 1 MVA, Determine the current drawn by the load in per unit to be computed at the first station of forward backward sweep load flow approach. So whatever the first uh, we will take the gas value at the nodes. So let the gas value visually take as 1 per unit. So let the gas value voltage at the first station be 1 per unit. Then the current drawn at was I can we can write as then current at was I is given by Pi minus JQI divided by VI conjugate. So using this formula we can find out the current drawn by the load in per unit at the first iteration. So for that we will find this power demands in per unit. So the per unit value of power demands of a node are active power is 80 kilowatt. Since the base volt ampere is 1 MVA, so we can write it as 100 kVA. So it will give you 0.08 per unit, and 60 kVAR is the reactive power divided by 100 kVA in the base value. So it will give you 0.06 per unit. These are the power demands at a node. So we are having the known values as active and reactive power, and we have taken the gas value of voltage at the node as 1 per unit. So we will put all these values in this equation. So the current drawn by the load in per unit at the first iteration is I bar. So take it as P minus JQ divided by V bar conjugate. P 0.08 minus J 0.06 V bar conjugate. So we have taken one and the angle of 0 per unit. So conjugate of this is also same. So it will be one angle 0 degree. So this will be the same value 0.08 minus J 0.06 per unit. So correct choice for this problem 7 is D. Yes. Payal, Pedro, Anu, all of you are correct. Very good. So till here, is there any doubt till this question number 7? If you having any doubt, then you can ask me. So now let us move to the next problem. So the next problem is what are the data of distribution lines required to perform the forward backward sweep load flow algorithm? So what are the data of distribution lines you require for performing the forward backward sweep load flow algorithm? And the options are line. This is multiple select question. In this question there are more than one options can be correct. So what are the data of distribution lines we require to perform the forward backward sweep load flow algorithm? And the options are line resistance, B option is line reactance, C option is line current, D option is line power loss. So what do you think? You can type your answer in the chat box. Pedro and Payal. Pedro has given response A and B, Payal C and D. This is very simple, just you have to recapitulate the things. So for distribution lines, what are the data we have given? Got another response A and C. So in what we usually do in the backward sweep, we find out the line currents. For finding the line currents, we use the KCL, Kirchhoff's current law, and in that we does not require the data of distribution lines. And further, while while doing the forward sweep, we determine the node voltages, and in that process we apply KVL, and for KVL we take this drop across the lines of distribution lines. So for finding out the drops across the distribution lines, we require the data of line resistance and line reactance. So this RNX we require. So the correct options are A and B. And these data are required during while we use the forward sweep, that in which we determine the node voltages. So the correct options are A and B. These data required while we use the forward sweep, and the forward sweep we use the KVL, Kirchhoff's voltage law, to find out the node voltages. So only Pedro is correct. Now let us see the next problem. So the next problem is the computation of forward sweep of forward backward sweep load flow algorithm starts with, and the options are the most distant node, and that is there beyond which there is no node. B option is substation node or slack node. C option is any intermediate node, and the D option is the node with the least power demand. So what do you think? You can give your response in the chat box. B, Payal, Pedro, Anu, all have given B. Yes, yes, B option is correct one. So in this question, it is asked about the forward sweep. Forward sweep means we are moving towards forward direction. So in order to move in the forward direction, what we will encounter first? We will go through the substation node or slack node. So that's why B option is correct. And let us see the next problem, question number 10. And this question is that similar to previous question. In this question, it is asked about backward sweep. The computation of backward sweep of forward backward sweep load flow algorithm starts with, and the options are: A option is most distant nodes beyond which there is no node. B option is substation node or slack node. C option is any intermediate node, and D option is the node with the least power demand. Pedro, Anu, Payal, Palvi, all of you have given answer as A. So yes, in the backward sweep, we move in the backward direction. So first it will start from the last node, that is most distant node, beyond which there is no node. So the correct answer is A. So in the backward, we move in the backward direction. You can say like that. So we will encounter first with the last node, the most distant node. So the correct answer is A. So we have solved all theoretical type questions. Now let us see the numerical type question. So the in this is common data for question 11 to question 13, and the data are given as for 5 node single phase radial distribution system. Load and line data are given on the following table. The voltage at node 1 is 12 at the angle of 0 degree kV. The load flow program is solved using forward backward sweep approach, assuming initial voltages at all the nodes to be 12 at the angle of 0 degree kV. and the line data and the load are given. So first we will make the single line diagram for this problem based on the data is given. So let us suppose this first node as substation node, slack node that is. In this radial distribution system, there are 5 nodes. This is first node. So second node. This is third node. So how we are assuming that how where is the line present? So you can see the line data. So line 1 and 2 are connected and having impedance value as 0.4 plus 0.7 ohm. These are the line data given. So accordingly, you can draw the line between the nodes. And again, we have the line between second and third node and having the impedance value is given as 0.3 plus j 0.4 ohm. Similarly, we have line present between the node 3 and 4 and the impedance value is given as 0.5 plus j 0.6 ohm. And the last line present is between the node 2 to 5 and the impedance is given as 0.3 plus j 0.4. So you have to make connection like this. So this impedance value is given as 0.3 plus j 0.4 ohm. This is all about this structure of radial distribution systems. And now we are having loads given at different nodes. So node J means at this J, so this one is common. So at second node we are having load given as 200 kilowatt plus 150 kVAR. So here we have to make we denote it as P2 plus JQ2. So this value is given as 200 plus J150. And here in this third node P3 plus JQ3. So at this third node we are having 500 kilowatt plus 200 kVAR. So 500 plus J200. And at this fourth number node 400 plus 300 kVA. So this one is P4 plus JQ4. 400 plus J 300, and at the node 5 300 plus 200 kVA. So this we denote as P5 plus JQ5 300 plus J200. So we take it as in this diagram we denote the line current. So the line current flowing between the these connecting one and second node we denote as I bar 1 2, and we denote this line current as I bar 2 3, and this we denote as the current as I 3 4, and similarly we denote this current as I 2 5. And what are about the load currents? So we denote the load current as for this load connected as node 2, we denote this current as IL2, and node 3 we denote this load current as IL3, and for this node 4 we denote this load current as IL4, and for this IL5. If you feel any doubt, then you can ask. And this resistant and reactance value we denote uh, corresponding to the connection between the nodes, like 0.4 and 0.7 is a R12 X12, and this is R23 X23. Similarly we denote this resistance value. So this is first we have made the single line diagram, and now we will see the problem. What are the problems asked upon this data? So the first problem is during the first iteration, the load current IL5 is. So this is little bit calculative. So you start solving this problem with me. So in this problem, we have to find out the load current IL5. So this one is straightforward, not that much calculative. You have to just apply this load current formula we have seen in the, I think, fourth or fifth problem. So initial voltages at node voltages we have assumed to be 12 at the angle of 0 kV. So IL5, how you can write? P5 minus JQ5 divided by V5 bar conjugate, and this value is the initial guess, that is 1200 at the angle of 0 degree kV. So we have assumed the voltage at all nodes is 12 at the angle of 0 kV. Here the we have given options in directly in not in per unit, directly actual values. So we will not convert these values in per unit. So we will use the real data only. So P5, how much it is given? P5 we have given as 300. So 300 minus Q5 is 200 kVAR. And V5 we have given as 12 at the angle of 0 degree. So what will be the value is coming? So it will come as 25 minus J 16.67. So we will get 30.05 at the angle of minus 33.69 degree ampere. So the correct option for this problem is A. Yes, Anu has responded only. So A option is correct. So while solving, if you face any problem, then you can ask in between. So next problem is, we will see the next problem, question number 12. And the 12th problem is, during the first iteration, the load current I12. So we have to find this current, load current I12. So for that, we have to just use the backward sweep. So for that, we need to calculate first, like if you need to calculate this I12, you need to calculate this all load currents, then you can get this I12. Summation of all nodes will give you the I12. So for that, we will first find out the IL2. IL2 P2 minus JQ2 V2 bar conjugate. So here in this question, it is asked about the first iteration. Then we will assume whatever the initial guess we have taken, the voltage we will take here V2. So P2 is 200 minus J150 divided by V2 bar 12 at the angle of 0 degree. Similarly, we can find this IL3, that is P3 minus JQ3 V3 conjugate 500 minus J200 divided by 12 at the angle of 0 degree, and IL4 we will find IL4 is P4 minus JQ4 V4 conjugate 400 minus J300 divided by 12 at the angle of 0 degree. And IL5 we have already found out in the previous problem. So IL5 you can write similarly, like we have wrote in previous problem, 300 minus J200 divided by 12 at the angle of 0 degree. So here it asks about the load current. Sorry, this is wrong here. This is not load current. This is line current. Line current I12. So applying KCL at this here at node 2, KCL at node 2. So you will get I12 line current is equal to load current IL2 plus line current I23 plus line current I25. So if you expand this, then you will get all the load currents simply. So IL2 plus IL3 plus IL4 plus IL5. So doing all this, like you will get 1400 minus J850 divided by 12 at the angle of 0 degree. We have just sum up all the active powers and minus sum of all the reactive powers and divided by the voltage values, initial voltage value. So you will get 116.67 minus J 70.83 ampere. So in phasor form, it will comes out as 136.49 minus 31.26 degree ampere. So option D is correct. Is there any doubt in this problem? Yes. So in this problem, what sweep we have applied? Here we have applied the, we determine the line current. So we have to apply the backward sweep. Unless and until you don't know the load currents and the line currents at the last node, and then we will move in the backward direction, then only we can find out the line current. So if you don't have any doubt, then we will move to the next problem. So the next problem is that at the end of first iteration, the voltage at node 5 V5 is what? So you need to find this voltage at this node 5. So for that, first we need to find out the voltage at the node 2. So here we will apply the forward sweep because we are going to find out the node voltage. So here we will apply the forward sweep, and for finding out the node voltage at node 5, that means it is the last node. So we need to find out the in between. So first we will find the voltage at node 2. So voltage at node 2 will be So V1 is the select node or substation node minus V1 minus I12 I12 and reactance impedance connecting impedance present at the line. So R12 plus JX12. So V1 we can write. So here you need to take care of the units. Like suppose 12,000 at the angle of 0 degree minus I12. I12 we have found out in the last problem that is that comes as 136.49 minus 31.26 degree, and R1 is 0 0.4 plus X1 is 0 0.7. Here you just need to do calculation and you can easily find out. So you will get the value as 87 at the angle of minus 0.26 degree. This is V2, voltage at node 2. So we can find voltage at node 5. The first iteration for that equation, KVL equation will be V21 minus the line current I25 R25 plus JX25. So we have find the this unit will be volt. So 11,903.87 at the angle of minus 0.26 degree minus I25. I25 we have found out I25 is equal to IL5. So I25 is equal to IL5. So IL5 we have found out as in the question number 11 we have found out the IL5. IL5 we have found out 30.05 at the angle of minus 33.69 degree ampere. R25 is given 0.3 plus, here you can see 0.3 plus J 0.4, and we have taken R12 and JX12 from here 0.4 plus J 0.7. Upon simplification you will get 11889.73 at the angle of minus 0.28 degree volt. In order to find this in kVA kilovolt, then divide it by 1000, then you will get 11.89 minus 0.28 degree kV. So the correct option will be B, 11.89 at the angle of minus 0.28 degree kV. Till here, if you having any doubt, you can ask. Otherwise, we can move forward to the next problem. So the next problem we have also based on the some data. So the data is given as here, and this one is the last one. We are going to solve four questions, and that we will then after that we will close our session. For this system again, we need to find out the single line diagram. So in this problem, for 6 node single phase distribution system, the table below provides the converged results. Means these results are final. Means after going through this forward backward sweep load flow algorithm, the final printed results we got is here given as of line flows using forward backward sweep load flow algorithm. The voltage at node 1 is 11 at the angle of 0 kV. So these are the data we got from after going through forward backward load sweep algorithm. These line flows, what are the currents flowing between the in the lines. So here we have 6 nodes. So here are the lines present. So based on the data, we can see that there is line between one and second node. So one and second. Then we have line between second and third. And then we have line between third and fourth. So this is slack node. First is assumed as slack node and second node, and this one is third node, and this is fourth node. And there is line present between second and 5. So here we can make one line between second and 5, and the line present between third and 6. So here also we can make 6 node, and the loads are present at all the nodes. We can take assume this as except slack node. So IL5, IL3, here take it as IL4, and similarly at node 6 the load current will be IL6, and at node 5 load current will be IL5. And the line currents we can take it as I12, I23, and I34, I36, and I25. So this is single line diagram for the following 6 node single phase radial distribution system. So let us see the first problem based on this data. So the question 14 is the voltage at bus 4 V4 is. So you need to find this voltage at bus 4. So we having voltage at node 1 is given. So at this node 1 voltage we have voltage given. So we have to find out the voltage at last node, the end node. So in order to that we will uh, apply the forward sweep. We will just apply the what you can say KVL. It's not better to write forward C because it is already the data. It is whatever the data we got after going through the load flow analysis. So it's so how we can find. So let us first find this voltage at node 2, V2 bar, V1 bar minus I12 plus into R12 plus JX12. So this data I12 is given. So this one is I12 and this one is I23 and this one is I34 and this one is I25 and this one is I36. So just putting all these value, V1 is given as 11 at the angle of 0 kV. So we will write all in a standard unit. So 11,000 at the angle of 0 degree minus I12. I12 is 157.89 at the angle of 21.1 degree. R1 to JX12 is 0 0.4 plus J 0.5. So from here you will get V2 as 10913 at the angle of 0 minus 0.267 degree volt. You may write it in kV. In kV divided by 1000, 10.913 minus 0.267 degree kV. Now we will find out the voltage at node 3. So V3 will be V2 minus I23 plus into R23 plus JX23. I23 is 88.08, 88.08 at the angle of minus 19.21 degree. R23 is given as 0.7 plus J 0.9. So we will get V3 as 10,828.85 at the angle of minus 0.558 degree volt. So we can also write it in kV form. So 10.83 at the angle of 0.558 degree kV. So now at the end we can find this V4. So finally V4 will be V3 minus I34 into R34 plus JX34. So V4 is equal to V3 will be 10,828.85 at the angle of minus 0.558 degree minus I34 be having given as 47.30 minus 12.1 degree into R34. R34 is 0.9 plus 0.9 plus J 0 1.1. So doing simplification, you will get V4 as 1077 10776.81 at the angle of minus 0.78 degree volt. So in kV form 10.788 you can write minus 0.78 degree kV. So the correct answer will be A. A is the correct answer for this question number 14. So this is very simple. You have to just apply the KVL and you will get, this is little bit calculative, but you need to have patience while solving this type of problem, and be just careful about the units, because you are not solve if you are not solving in per unit, then you need to careful about the kV voltage. So let us see the, so how many of you have tried this problem? So at node 2 you have taken IL feed should be IL2. Yes, correct. Thank you. I think it is not erased. So this one is IL2. So let us see the next problem. So in the next problem, the voltage at bus 5 will be. So it is asked about this voltage. So we have found out in the voltage at node 4. So in this question we have to find this voltage at node 5. So again we have to apply one KVL equation. You can also try yourself. So V5, how you can write? Voltage at node 2 minus I25, line current flowing between the nodes 2 and 5, and the impedance values, it will be multiplied. Just we will write this KVL equation and we will get V5. So V2 we have already found out. V2 we got 10,912.76 at the angle of minus 0.267 degree. V2 minus I25 is given. This one is I25. So I25 is 33.17 at the angle of minus 34.03 degree, multiplied by R25 is 0.7 plus J 1.0. So just find this V5. So if you Find this value, then in voltage form it will come out as 10,825.032 at the angle of minus 0.34 degree volt. So in final in kV we will get 10.87 at the angle of minus 0.34 degree kV. So correct answer will be D, 10.87 at the angle of minus 0.34 degree kV. So if you don't have any doubt, then we can move to the next problem. Problem number 16. Problem number 16 is the voltage at bus number 5 is the load at bus number 5, sorry, not voltage, the load at bus number 5 is. So we can use that current equation. We know that IL5 is equal to P5 minus JQ5 divided by B5 conjugate. There is no need to remember this formula because this you can derive it yourself. Like if you having, if you know that how you can write apparent power V into I conjugate. So if you are finding out this voltage at node 5, then V5 into IL5 is the current, load current. So this one is conjugate. So S5 we know P5 plus JQ5. So V5 into IL5 conjugate. So from here you can get this one formula. So there is no need to remember this. You can easily derive it from this simple equation. So here we need to find P5 minus JQ5. Otherwise you can also use this one. So if you go by this basic one, then we need to find P5 plus JQ5, and B5 we have already found in the last problem, that comes out as 10.87 at the angle of minus 0.34 degree, and IL5 we have calculated. IL5 is IL5 is 33 point. This IL5 is similar to IL2. This I25 is equal to IL5 is equal to I25. That is 33.17 minus 34.03 degree. So if you will take conjugate of this IL5 conjugate, then just reverse the sign of angle. So it will be 34.03 degree. So 33.17 at the angle of 34.03 degree. So voltage in is in kilovolt and current is in ampere. So final answer we will get in kVA. So P5 plus JQ5 will comes as 300.15 plus J 300.16 you can bet plus J 200.07. So P5 plus JQ5 approximately equal to 300 plus J200 VA kVA. So correct answer for this question number 16 is B, 300 plus J200 kVA. I think you are able to get this question. If you face any problem, then you can ask. Now let us see the question number 17. So try this question yourself. So in this problem, it is asked for voltage drop between bus 3 and 4. So this is also not that much difficult. You just have to subtract the voltage at bus 3 and the voltage at bus 4. So voltage drop will be VD. We can denote VD 3 4. So voltage drop is V3 minus V4. So V3 we have calculated. V3 comes as 10,828.85 at the angle of minus 0.56 degree minus this is V3 and V4 we have calculated 10,776.81 at the angle of minus 0.78 degree. So this will comes out as 67.23 at the angle of 38.61 degree volt. So option C is correct. Now let us see the last problem of this session. So the last problem is that you need to find out the total power loss in the distribution system. So we have given the line current. So what we need to do? We have to use that formula I square R. So we have given this I12 and resistance value is given here 0.14. Then just multiply the magnitude with a square of magnitude of current with the resistance value. I23, this one is I34, this one is I25, this one is I36. So this last problem means question from question 14 to 18. We are just seeing how this load flow analysis helps in analysis, finding out these various characteristics like voltage drop, power loss, and the voltage at the various nodes. So we are doing that only thing. So we can write power loss is equal to power loss is equal to I12 square R12 plus I23 square into R23 plus I34 square R34 plus I25 square into R25 plus I36 square into R36. So finally we are having power loss as I12 is 157.89 ampere square into R value 0.4 plus I23 is 88.08 square into R23 0.7 and I34 is 47.30 into 0.9 and I25 is 33.17 square. R25 is 0.7 plus plus I36 is 41.56 square into 1.0. So this will give you total power loss. So is there anyone who have calculated the value? What will be the value of power loss? So just simplify this. You will get the final total power loss in the distribution system in the given 6 node single phase radial distribution system. So you will get 19,913.33 watt. So in kilowatt you will get 19.91 kilowatt. So option B is correct. So if you have any doubt you can ask. Otherwise we can close today's session. Okay, all right. So thank you all for joining this session and we will meet on the next Saturday at the same time. Thank you all.